Okay, so this is meant to be a quick video to go over the day 6 problems, and it's going to go pretty quick, but feel free to pause and catch up if you need to. So problem 1 says to solve for x and y, and you're going to want to solve in terms of t. And after a couple steps of algebra, we can get to this, and you're done. So for 2, we're given a situation with a bug crawling across the paper. This is the first time we've seen something involving parametric equations. So what I'm going to do is come up with the equations that describe the motion of this bug, and with that you should be able to answer all parts of this question. So first we need to have some basic equations. I've written an equation for x and y, each in terms of t, which is what the parametric equations are going to have us do. Instead of having x and y being in the same equation, where x is your independent variable and y is your dependent variable, in this case we're going to come up with two equations where t is always the independent variable and x and y are your dependent variables. So in this equation, we've got m1 and m2, which are the rate of change between t and x and t and y respectively. And then it's always important to remember that the b1 and b2 that I've written into these equations are the starting points where your x and y values are at t equals 0. So next what we're going to do is plug a point into each of our equations in order to solve for the rate of change, that m1 and m2. So I've picked the point t equals 10, which corresponds to 3, 5. Any of the points will do. I just picked the first one I saw, other than t equals 0. So now what I've done is plugged into my x and my y equations. I've plugged in the time, which is 10 seconds for both. I've plugged in the x value at that time, which was 3, the y value at that time, which was 5, and I inserted the starting points for each equation. So the starting point for x, right here, right where t equals 0, is 1, and for y, it's 2. After some algebra, you get to m1 being 1/5 and m2 is 3/10, and then the final step is to put all of this into one equation. So here what I've done is I just took the m1 and m2 that I solved for and put it back into my original equations here for x and y, and I put the starting points in. So this equation here tells me how x changes as t changes, and this equation here tells me how y changes as t changes. And you can use both of these equations to plot the bug's motion for any time you want, which is what's going to help you answer parts C and D. And if you want to get really fancy, you could write it like this, where you've got the position, that's all this means is position, and our independent variable is t, is going to be, this is our x. Notice our x component is the same as our x equation, and our y component is the same as the y equation. So you could just plug t in there once and get a point, say, for when the bug, where the bug is at 26 seconds. And that should help you get through problem 2. For number 3, all you should need is the midpoint formula, so it's right here. And I'll do part B for you because I think that might be the more confusing part of this problem. So all you're going to do is add up the x components, divide by 2, add up the y components, and divide by 2. Make sure you're careful with the notation. It is an ordered pair, so you need parentheses, and you need the comma in between. So for 4, we're given 3 points, -1, 5, 5, 2, and xy. And we're asked to write an equation that determines the distance from xy to -1, 5, and then a separate equation that asks us to find the distance from xy to 5, 2. So I've just drawn those representation of those distances in, and we're asked to say that the xy is equidistant from both those points, so that would mean that d1 is equal to d2. So if I write out equations for these distances, it should look something like this. Remember, the distance formula is identical to the Pythagorean theorem, just rearranged a little bit. So if you need to go back to Pythag to figure this out, that's fine too. But here are these distances written in distance formula. And what I'm going to do is substitute in. So I've got this is d2, this is d1. I'm going to sub both of those back into this equation where d1 equals d2. And that's going to look like this. And then after some algebra, we should get to a nice equation. So after a whole bunch of simplifying, we get down to y equals 2x minus 1/2. And what is y equals y equals 2x minus 1/2? That's going to end up being this line right here. I'll try and draw it as neat as I can. It's not going to be perfect. We get that line, and if you remember from previous problems, that should be the perpendicular bisector between the 2 points, because that'll be the set of all points that are equidistant from both of them. In problem 5, we were asked to look at line ax plus by equals c, which looks like it's in standard form. And we're asked if we can find a line that satisfies that equation and doesn't have a y-intercept or doesn't have an x-intercept. So initially you should be thinking vertical and horizontal lines. So if I have a vertical line, that is going to have an x-intercept, but it's never going to cross the y-axis because it's parallel to the y-axis, and parallel lines never intersect. So we have a line here that does not have a y-intercept. How could we reflect that in our equation? And what I want us to try is, let's let b equals 0 in our equation. What would happen then? We'd have ax equals c. So we can clearly see that if y is 0, we can find our x-intercept, right? Because isn't that how we find intercepts? So we would just solve for x, and it would be c over a. So in our line, we would cross here, this would be c over a, whatever c and a are. So we have an x-intercept. But let's rewrite it, let's look back up here. What happens if I let x equal 0? Well, if I let x equal 0, let's do that over here. If x equals 0, then we get 0 equals c. And that isn't going to be true, right? So that's an undefined quantity, which means that we don't have a y-intercept. So there's the answer for the first part. And you can do the same logic puzzle for the second part. It's just going to be a horizontal line. So I'm not going to talk about 6 and 7, but for number 8, we've got another one of those bug going across the paper problems. So what I've done is I've graphed it pretty sloppily, but it's there. And what we're going to do is just jump right into finding the equation of the parametric equation for this problem. So remember, we're going to start here, and this is the rate of change between x and t. This is the starting point for x, rate of change for y and t, starting point for y. So I'm going to plug in those values. And now the next thing I need to do is pick a point other than where t equals 0 and plug in those values to solve for m1 and m2. So that gives me m1 and m2, and then the final step is to plug it all into our position equation. And once we have this, we can plug in any t we want and find the coordinates. For part B, where the object is equidistant from the coordinate axis, we need to look at what represents how far we are from each axis. And what that is going to look like is these values here, right? This is how far we are from the y-axis. This is how far we are from the x-axis. So if we set those equal to each other, we should be able to find the time where they are equidistant from both axes. So what I've done is set them equal to each other and found that t is 1. And then in red here, I checked to see if I was equidistant from both axes. So I plugged 1 into my position. So that means I plug 1 wherever I see a t, solved, and I got 6, 6. So that would mean it's equidistant from both the x and y axes, and the distance is 6.